Hi guys, and welcome back to the ACE Academy. In this video, we will be going over the superposition theorem for transverse pulses. In the previous video, I covered what a transverse pulse is. I explained to you guys how a transverse pulse is created and how it propagates through a medium. In this video, we are going to be investigating what happens when two pulses cross. Now, this phenomenon is governed by a simple theorem that we call the superposition theorem. And the superposition theorem essentially states that when two pulses cross, their amplitudes add to result in a single pulse. Now, I just stated that to you guys. I didn't show you any examples so far, so that's going to be a bit fuzzy at first. But of course, we are going to delve into this section, and I'm going to show you what I mean by that statement step by step. So firstly, if you guys want to take that down, put it in a book somewhere, you can of course take it down. I have it zoomed in on your screen. So the superposition theorem states that when two pulses cross, the amplitudes add to result in a single pulse. But the more important bit that I want you guys to focus on is that after these two pulses cross, they will continue to travel in their initial direction and at their initial magnitudes. So let's do a little investigation together. The first thing that we are going to do together is something that is known as constructive interference. And this is what happens when two pulses cross and they are on the same side of the medium. What I mean by that is the amplitudes will be in the same direction, and these two waves will be in phase. When I speak about a pulse being in phase, we are talking about the fact that their crests will line up. Now, in case you guys do not know what a crest is or what a trough is, I just want to highlight that for you guys quickly on the diagram that I have drawn out. When I am talking about a crest or a peak, I am talking about this shape right here. Now, that shape is created when a particle on a medium has a positive displacement. When I talk about a trough, I am talking about this shape right here at the bottom, and this shape is created when a particle on the medium has a negative displacement. In order for you guys to see it visually, I want you guys to think of a crest as a little hill, and I want you guys to think of a trough as a little bowl, right? That's how you're going to differentiate. Now, of course, like I said, we're doing superposition theorem, so let's focus on that. Let's not divert from the topic too much. Let's look at our first example. In our first example, you guys can see that I have two pulses on the same medium. I have the one on the left being highlighted in red, or drawn in red rather, and I have the one on the right being drawn in blue. Now you can see that these two pulses move towards each other. The red one is moving from left to right, and the blue one is moving from right to left. Eventually what's going to happen is these two pulses are going to meet at some point. And our entire investigation is to figure out what happens when these two pulses meet. Now, in order to do that, I'm going to move over to the next diagram that I have drawn out for you guys. And as you can see, I have created a single pulse that has quite a high amplitude. So what we're going to do together is we're going to focus on how these amplitudes relate to the individual pulses. Let's move back to the first diagram that I have. Let's look at the amplitude of each pulse. We can see that for the red pulse, it will have an amplitude of 2. It's aligned with 2 on the y-axis. And for the blue pulse, it will have an amplitude of 1. That's because it's aligned to 1 on the y-axis. Now let's go ahead and look at what happens when those two pulses collide with each other. We can now see that this new pulse will have a new amplitude of 3, which is corresponding to the y-axis. Now, why does this new pulse have an amplitude of 3? That is simply because all we had to do was add up the individual amplitudes of both pulses, and we would get the resulting amplitude of the new created pulse. So let's do that quickly just to check it. We can see that on the first diagram, the pulse on the left, the red pulse, had an amplitude of 2. So let's write that down quickly, 2. And let's look at the amplitude of the blue pulse, which is the one on the right, that had an amplitude of 1. So we'll add that to 1, and we will get a result that is equal to 3. So if we have a new amplitude of 3, let's check if that corresponds to the created pulse. And what do you know? It does. The amplitude of the newly created pulse is 3. Now, my next question to you guys is, what would happen if these pulses continued passing each other? How would that affect the way that the pulses travel? Let's have a look at it. We can see that after that initial combined pulse was created, the individual pulses break apart and they continue in the exact same direction that they initially were traveling in. So we can see that the blue pulse is now moving from right to left as it previously was. The red pulse is moving from left to right as it previously was, and they have their original amplitudes. So essentially what we are saying is that when two different pulses superimpose or collide, it will result in one large pulse, and as time progresses, those pulses would eventually break apart again, travel in their original direction with their original amplitudes. It's quite simple. I hope you guys didn't get too confused with the way in which I explained it. Let's move on to the second type of constructive interference, and that is when we have two troughs moving towards each other. These are two pulses with negative amplitudes. We can see it does the exact same thing. Let's look at the amplitude that each pulse has initially. We can see that the red pulse has an amplitude of -2. The blue pulse will have an amplitude of -1. And now let's do a little investigation. Let's see what happens when I add those two values up. So I will do -1 plus -2, and I would get an answer of -3, which means my resulting pulse would have an amplitude of -3. And hey, what do you know? It does have an amplitude of -3. That simply tells us that in order to get the resulting amplitude of the created pulse that has been created from two separate pulses, all we would have to do is add up their individual amplitudes, keeping in mind you have to take the sign with the amplitudes. You cannot leave it out. Okay? Now, of course, let's see what happens once these pulses break away. And as we can see, they broke away into their initial pulses. They have the same properties, same amplitude, they move in the same direction. It's quite simple, guys. So that was simply your constructive interference. That is where the resulting pulse is larger than the individual pulses that make it up. Right? Let's move on to destructive interference. Now, destructive interference is kind of a special case. This happens when your pulses are on opposite ends of the medium. They have a difference in amplitude where one would be positive, the other would be negative. Now, in a similar way to constructive interference, all we would have to do is add up the amplitudes of the individual pulses to get the amplitude of the combined pulse. And in order to do that, we have a couple of diagrams for us to work with. Of course, initially, this little diagram, the red pulse has an amplitude of 3. The blue pulse has an amplitude of -2. Let's look at the combined effect when these two pulses cross over each other, when these two pulses superimpose. You can see that the resulting pulse has an amplitude of +1. Now, where did we get this +1 from? All we did is we added the +3 from the red pulse to the -2 from the blue pulse, and we got a resulting pulse amplitude of +1. Now, I want you guys to also take note of one more thing, and that would be the fact that the side that has the larger pulse will ultimately be the side on which your resulting pulse would be on. The created pulse would be on, right? And of course, we can see after they superimpose, they will of course go back to their original amplitudes traveling at the original direction. Same thing with the second diagram in this section. We just added up the amplitudes, got a resulting pulse, and then they broke apart and continued in their original direction. Now there's a special case of this theorem that I want to investigate with you guys, and that is the scenario in which the pulses are on opposite side of the medium rather, but they have the same magnitude, they have the same amplitude. What would happen in that case? Simply, the pulses would cancel each other out once they superimpose, and after they superimpose, they will continue with their same magnitude and in the same direction. It's quite simple, guys. That's it from me. All the best, and I will see you in the next one.